right, let's go and review some things we talked about yesterday. I began looking at really the only non-polygon we care about as far as a geometric figure, closed figure. And what was that, Audrey? The circle. And again, it may not be textbook definition, Audrey, but what is a circle?
It's a closed kind of with center.
And how does the curve relate to that center point? All the points that are in the curve all have to be what?
Aren't they fixed points?
Well, the fixed point is the center, and then you said it's a closed curve. So, this is a closed curve, right? That's a closed curve. Okay. Also an amoeba. And so there's a center point, right? But what would make it a circle is if every single point in this closed curve was. Kendall, can you help her?
Equal.
Equally. Genesis?
Round.
Yeah, Ethan?
Equally distant.
Equally distant from that center point, because further, closer, they're not equally distant. That's why not a circle. So it's a closed curve that we need to make sure we account for that, right? Closed, meaning it completely encloses, as opposed to that. That's not a closed figure. It's a curve, okay? Which means it's not going to be bounded by any straight lines, with a fixed point as the center, and all the individual points are equally distant from that fixed point. That's the key to know. So if we were to have a circle, and we'll just pretend for a moment that that's a circle, if we were to draw a line showing that distance from the center to any point on the circle, we've drawn something, Kendall, called a radius. Very good. If I were to draw a line that happens to have its ends on a circle, Genesis? Not a diameter unless it goes through the center. Then it's a diameter. But what do we call this line, Chris?
That's a chord.
A chord. Very good. So a chord, remember, just has its ends on the circle. The diameter specifically goes through the center. By the way, this is a radius, but so is this and so is that. We have then three, what's the plural of radius, Ethan?
Radii.
3 radii in our picture here. Very good. Now, of course, the circle is this curve right here. It's not the stuff inside it. That's just stuff enclosed by the circle. The circle is literally this bunch of little infinitely small points that come together to finish off the curve. If I were to take just a limited portion of that curve, say from here to here, we have something called, Genesis, an Noah built one of these. Ark. Okay, only it's spelled different. For Noah, it was A-R-K, and ark like this would be A-R-C. Not A-R-C-H, that's an arch. Okay, that's like a covering thing that happens to have an arc at the top of it, but an arc, okay, a limited portion of a circle. Now, we said that if we were to draw an arc that literally is half the circle, that arc is specifically called, we'll come back to Genesis 3rd tries the charm, very good, a semicircle. Very good, a semicircle, half the circle. And if I were to cut that in half, I would have an arc equal to 1/4 of a circle, Ethan, called a?
You're calling me on the one I didn't remember.
Good geometry term here, by the way. There's 4 sections here. Well, if you were to take half of a half, you get 4 equal sections here. Each section is called a, Audrey? Quadrant. So if you can think back to geometry or algebra days of quadrants on the Cartesian plane, think quadrants, if you will, on a circle as well. 4 sections that are equal to each other. What about the distance around a circle, Chris? Called the circumference of the circle. Very good. What's the geometric instrument used for drawing circles and arcs? Kendall? The compass. Very good. Yesterday we made what observation about all radii within the same circle? Genesis? They're all equal to each other, and it took us a long time, but what conclusion did we come to about diameters in the same circle, Audrey? And why did we show that they had to be equal?
Because the circle was perfect.
Uh-oh, we're gonna go through this again. We don't have time for this today. Ethan?
Because the two radii equal what?
Good. A diameter just equals 2 radii. So because a diameter equals 2 radii, and we'd established based on the definition of what a circle is, all radii have to be equal, then that leads us to concluding diameters are equal as well. Turning books page 26, we were trying to work through these questions, and we got through 3 of them. So we need to finish the last 9 of them that we were supposed to do yesterday in short order today. Number 4 question says, show that a radius is half a diameter. This kind of builds on what we already showed yesterday, right? Question?
I was gonna say how to do it, but then I realized that too late.
Okay, we more or less approached this yesterday, so kind of building on what we showed yesterday, Chris, how would we show that a radius is half a diameter?
Draw a circle with no radii.
Without drawing anything.
Cut a diameter in half.
Okay, and by cutting it in half, we get what?
A radius.
Where is a diameter cut in half?
Circle. At the center point.
At the center point, there we go. Any diameter, right, is going to be cut in half at that center point. Each half is a radius, therefore a radius is half a diameter, so pretty straightforward there. Number 5 says show that any 2 diameters bisect each other. Well, within a circle, where do all the diameters have to intersect, Genesis? Now we don't call it the middle, at the center, very good. So in any circle, no matter, we said, how many diameters can we draw in a circle, Genesis? An infinite number, but any diameter you draw is going to have to pass through that center point. And because all diameters intersect at the center point, and all diameters are divided into 2 equal radii at that center point, when something is divided into 2 equal pieces, we say it is bisected. So we would say all diameters will bisect each other at the center point. If you would, go ahead and take out your compass and a sheet of paper. Keep your desk there near you, or your book there near you on your desk, and keep your desk near you. That's kind of hard to get away from if you're sitting in it. Go ahead and draw a circle on just an extra scrap sheet of paper. This doesn't have to go in your notebook. But let's start with an actual circle here. By the way, you don't draw, remember, with your compass the way I do with mine. You don't hold the top of the compass, Ethan. You don't hold the top of the compass. I only do because I have something that's on the wall. You're going to hold your compass down here and just rotate it in your fingers. But also, you can spin the paper. I know I had, again, the downside of holding at the top, Audrey, is you're more likely to push down with it. So just hold the pointy end. All the weight of, all the pressure of your hand should be at the pointy end of the compass to keep from risking the paper, the compass slipping or something. So hold that pointy end. Again, spin the paper, right? My elementary teacher's like, don't spin the paper. Why not? It's the easiest way to make the circle perfect. By the way, a tip for you. As you're drawing on your paper, I want you to watch my compass. If I'm drawing on the paper, I don't hold my compass straight up and down. I angle it into the rotation. So as I rotate the paper, it's giving. So the paper moves this way and allows the compass to give. You hold it straight up and down, it might catch and do that thing across the paper. If you angle the compass a little bit, that'll help you as well to get a nice smooth circle. So just a couple of tips as we'll be doing a little bit with circles here. All right, so you've got a circle. It says draw in it a diameter. So with your straight edge, go ahead and draw a diameter, meaning remember any chord that goes through the center. You should have a little hole in the paper or a little indent in the paper where the point of your compass just was. So using that, make sure your line goes end to end, which means it's a chord. Make sure it goes through the center, which means it's a diameter. And then it says select any point in either semicircle. Pick any point in either semicircle. So we've got a semicircle above the diameter, we've got one below the diameter. Do you want to go above or below here at the board, Kendall?
Above.
Above? Okay, to the left or to the right?
Right.
To the right. So somewhere over here? Not lower, not higher? Okay, it's not like I'm doing a magic trick or something, right? Are you sure you want to pick that card? You have a free choice, right? You can pick any other card you want. All right, so pick any point in either semicircle, and it says join it, that point, with the ends of the diameter. So connect that point that you picked at random to one end of the diameter and to the other end of the diameter, basically forming a triangle here. The question is, what kind of angle is formed right here. We'll take your protractor now and measure this angle. We'll take your protractor and measure your angle. And let's see what we wind up with here. I got 90 degrees for mine. Audrey, what did you get?
90.
You got 90 also, okay. Kendall?
90.
You got 92. No, I'm not 92, you got 90. Chris?
108, no, I got 90.
You got 90, okay. Ethan?
Let's say 9 degrees.
You got 90, okay. This seems to be a pattern here. Genesis is measuring, or completing here. But so far, I mean, we all drew different size circles. We all picked different points. Pick a different point. Maybe one like toward the middle or something this time in the other semicircle. Let's see if it still gets 90. Maybe it's just because we went on the top. Maybe if we'd gone on the bottom, it would have been different. So, because I don't want to draw a conclusion without some sort of testing here. But we did all use different sizes of circles. So. Yeah, I still got 90. Anyone else still get 90? Audrey did, Kendall did. Genesis, did you get 90?
For the first one?
For the first one? Yeah. Alright, Genesis got 90. Chris is saying he got 90. So, seems
90.
like, now this doesn't prove anything, right? But it sure seems like if you were to connect any point in a circle to the ends of a diameter, it would end up giving you a 90-degree angle. Alright, let's draw another circle. Draw another circle. I think a good sized circle, don't make it too little or anything. Go big or go home, as they say. Alright, so nice big circle. I'm going to mark my center point again. You've got a little indent on your paper there. And draw any chord that's not a diameter. Pick any chord. Let's see, we're going to go, I just called on Kendall, but Kendall, do you want a short chord or would you rather a longer chord?
Long.
You want a long chord, but not a diameter, right? So maybe right about here. Is this a nice long chord right here? Okay, so we're going to go with a nice long chord. I was sure you were going to say short. All right. So we draw a chord, and then it says at one end, draw a second chord at a right angle. So take your protractor, and I'm wishing I'd drawn it sideways instead of straight up and down. Take your protractor, and at one end of it, I'm going to go at the bottom end, make a 90-degree angle. At one end of it, make a 90-degree angle. At one end, make a 90-degree angle. Now, my 90-degree angle cut outside the circle, as you can see here, but it touches the circle, it hits it right here, okay? So, find the point where your right angle hits the circle so that you've got another chord. I'm going to scribble out the excess. So, a perpendicular chord, if you will. The question is this: if I were to join this end of the perpendicular chord to the free end of the original chord, will this line go through the center of my circle? Will that line go through the center of my circle? Mine did. Audrey's missed just a nudge.
Mine missed just a nudge.
Yours missed just a nudge. Let me do this. Let me make a shorter chord this
I
time.
missed barely.
You missed also? Do a shorter chord this time. Once again, at one end of it, I'm going to go to the let's go to the left end here. Go ahead and do a right, make a right angle. Alright, so get your right angle. And once again, you've got two free ends here. Connect them. See if it goes through the center of the circle. Mine just kind of nicked the edge of my center dot there. Anyone get it to go through the center this time? Audrey's still missing. Chris
I
is still
missed a
missing.
ton.
If you did it perfectly, it should. Now, we're gonna prove that later. For now, though, if we were to go off our observation, we would agree, no, it doesn't hit because most of us have been missing. Again, this is one reason why we can't just go off of measurements with instruments and assume conclusions from them. But we're gonna prove later, if you did it right, Chris, that's not a chord.
From right here to right here, it's not a chord.
Chris, okay.
From right
When you
here.
drew the perpendicular, you were supposed to make a chord with it.
Is that not a chord?
No, you make a chord, and then you make a perpendicular chord, Chris, and connect the ends of the chords, and see if it goes through the center. It's okay, just, you gotta learn to listen. Alright, we move on though, we move on. Number 8, draw another circle. Draw another circle. You're gonna get good at drawing circles by the end of the day, if nothing else.
For real.
Draw another circle.
Oh, man, I did
I'm thinking one.
And, you know, decent size, you know, maybe a couple inches across, a couple few inches. Go and draw a diameter. Do one like this time. And draw a diameter. Ruler's foot. And then we want to draw another perpendicular diameter. So what we need to do is go to the center of the circle, line up the protractor, and make a 90-degree perpendicular diameter. So we're going to make 2 perpendicular diameters, like this. It's a little slanted here, Ethan, but if you wanted to picture this, you can picture a little XY axis there to get your true perpendicular number lines. A little flashback to algebra, just for those of you who've been missing it. And it says, join the ends of these diameters. So connect the ends of these diameters. All of them? Yep, all the way around. And what do we get? Appears to be a square. Now, if we wanted to do it right, we could measure with our compass, measure one side of what we think is a square, see if the next side is a square. Mine's a little off. Next one, and the last one, see if it really is. Mine's just a nudge off. Of course, I did have that issue right here where my ruler started to slip a little bit. And we get an actual perfect square. All the sides measure out. We'll measure those sides. Chris is saying, you got one?
Appears I do.
All right. Question.
Yeah, I did too.
What would we call that arc right there?
A quadrant.
It's got to be a quadrant, right? Because what did we do? We divided the circle into 4 equal arcs, which means it's a fourth of a circle, meaning it's a quadrant. Hence, Ethan, why I drew the X and Y axes to help you see the quadrant thing there a little bit better. Number 9. Number 9, draw a circle. This time, don't make it too big, and don't close your compass once you've drawn it. So draw the circle, keep your compass open the exact same amount once you're done. So not too big, maybe open it 1 inch at the most. Just because I don't need it to be bigger this time. Pick any random point on your circle. I'm going to put a dot at, what is that, about 130, 115, like that. Put the point of your compass on the dot that you made. Put the point of the compass on the dot that you made, and measure to a new spot on the circle with your compass. Then go to the new spot that you made, measure, pick another new spot. Then, point of the compass on that next spot, make another spot. And just kind of keep going around the circle, measuring off this amount. You should, if you did it perfectly, and I missed by about a 1/4 inch, they should come back around to hit the same spot you started at. You should come around and hit the same spot you started at if you did it right. How many actually, like you can see I barely missed here, about a 1/4 inch up. How many just nailed it?
I missed about a millimeter.
Okay, all right. So what I'm going to do is I'm going to enlarge the dot and make them hit, okay, just for sake of ease. What I want you to do is connect all those markings as you go around with little chords. Connect the markings with little chords. And what you should have is a regular hexagon. So a quick, easy way to construct a regular hexagon. Notice I did say construct, not draw, because you didn't use any tools of measurement, did you? Unfortunately, you can't use this method to construct anything but regular hexagons. So if you want an octagon, a heptagon, a pentagon, it doesn't work. This only makes hexagons, but kind of a neat way to do it.
I remember it.
Question for you now. This line right here, if I call this point A and this point B, that length, AB, is equal to all of these other lengths. But it's also equal to another length that we never drew. What else is it equal to, Chris?
The distance to the center.
The distance of either point to the center. We call this distance to the center class the radius. So if I were to draw both of these, I would have what kind of triangle?
Isosceles.
Better than that,
Equilateral.
equilateral. Because all these lines are equal. Right? We just had the radius length is what we used, and we kept that same radius length as we went from point to point. So how big are each of these angles? 60 degrees. So how big is this angle?
60.
And 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 if you were to add all 6 of those 60s together, you would get the 360 degrees at the center of a circle. And that's another reason, by the way, why it has to be a regular hexagon, because you have the equal angles all throughout. Number 11. Go ahead and draw a 1.5 inch line segment using your ruler. 1.5 inch line segment. Draw a 1.5 inch line segment. Call it A, B. Call this 1.5 inch segment A, B. Now we want to draw the perpendicular bisector of AB. Perpendicular just means what, class? Right angle, correct? Right angles, perpendicular. So we know we need 90-degree angles. But it also wants us the perpendicular bisector, meaning it's got to go right through the
Center. Middle.
midpoint, right? It needs to go through the midpoint of the line. Well, if it's 1.5 inches, what's halfway up 1.5 inches?
0.75.
0.75, 3/4. So measure the 3/4 inch mark and make a little mark right at 3/4 inch. Make a little mark right at the midpoint. Now again, this isn't, however accurate it is, it's still based on measurement, but I think it'll be close enough. And then at this midpoint, line up your protractor and let's make a 90-degree angle. And that'll get us a perpendicular bisector of AB. Alright. Now pick any random point on the perpendicular bisector. We're going to let Ethan pick here. Do you want to go above or below my line AB?
I don't know.
Below? A lot below or a little below?
A lot.
A lot below. So let's go down here, a good distance below. And hope this fits on the chalkboard. Measure from this point to B. Now, draw a circle and see if the circle also goes through A. Oop. See if your circle also goes through the end point A. Mine just barely missed the end point. How many for you, it went right through the end of A?
I did.
Yours did? Good. Anyone else went right through A? Genesis did, good. How many, maybe like mine, you can tell just barely missed. There's a tiny little bit of white showing, just barely missed. Again, what could we attribute that to? User error. Good, so it seems like, let's try another point. This time let's go above and just a little bit above. Let's do the same thing. Measure to B. If I can find where B went, I think that's it right there. Kind of covered up by the mark that's got to be there. Okay, and then again, make a circle. And this time I hit point A right on. Kind of like a snowman now. Anyway. So his head is sinking into his body, but you know, happens sometimes. Use the force. Reach out with your feelings. Alright.
Mine went right there.
So it seems like if you pick a random point on a perpendicular bisector, you could put a circle through the ends of the line. That's what it would appear to show us here. How many circles do you think then we could draw that go through these 2 points?
Infinite amount.
Infinite. So through a point, how many straight lines can you draw?
Single point, you draw one.
Through a point, how many straight lines? Infinite number. Through 2 points, how many straight lines can you draw?
One.
Only one. Through 2 points, how many circles can you draw?
Infinite.
Infinite. But the centers of those circles would have to be on the perpendicular bisector. Kind of an interesting thought. Okay, so that's at least what seems to be the case. That doesn't prove anything, but it seems to be the case. We're going to prove, by the way, these discoveries as we go throughout the course. Just kind of throwing a teaser out there, different things we're going to prove later. For now, we're just kind of observing they seem to be so. Terms definition section of notebook. Set that paper away. And terms definition section, we're going to move back off of circles for a little bit. I'm going to have you copy down this term in your notes. Congruent figures. Congruent figures. Now, you're going to write the word congruent, and then I'm going to give you the shorthand. You're never going to write that word again in your life. You're always, from here on out, going to make an equal sign with a squiggle on top. An equal sign with a squiggle on top. That's the symbol for congruent. Congruent figures, or congruent figs. Congruent figures are plane figures which have the same size and shape. Plane figures which have the same size and shape, and their